Hi everyone, here is our final project. Our motivations is to use climatic factors such as wind directions and speed, pressure, and humidity on the previous days to predict if a location in Australia will rain the second day. And for daily use, our model can work as a reference for people to dress tomorrow and help people prepare for the need of bringing umbrellas. We can help business to make better decisions and help farmers to get prepared for weather hazards.
So the data we have is from Australian government website. The original dataset contains 145K daily weather observations from stations across Australia in 10 years. We randomly sampled 5,000 weather records. Then we did some sanity check on the data. We look at the percentiles of each column. The gaps between minimum and 1 percentile and between maximum and 99 percentile are not very broad. Then we believe there's no outliers in our data. There's a column rainfall in the data describing the amount of rainfall for the day. From the histogram on the right, we can see about 60% of the data are in the range 0 to 10 millimeters. We convert this column into a binary categorical variable by thresholding at 1. Since the rainfall is seasonal, we extracted the months from the timestamp column and created dummy variables. The granularity of the data is reduced from daily data to monthly data in that case.
Next, we need to deal with the tricky feature named location. The location variable represents the common name of the location of Australian weather stations, and there are 49 different types in it. We want to map the location features to a new feature with less types. Our logic is to use the web crawler to find out all Australian city and weather stations detailed location. Then, by using distance calculation, we can find out the nearest city to the weather station. Finally, we map the weather station location with the climate. In this way, we get a new feature named the climate, which only contains 7 different categories. Next, we need to deal with all the missing values. Generally, most of the features have missing rate less than 10%. Some features such as evaporation, sunshine, and extra have about 40% of missing rate. For categorical missing values, our strategy is to use the most frequent category to replace the missing values. For the numerical missing values, we use the mean values to replace them. Last but not the least, we will encode and normalize the data. This step is very important because we will use unit-sensitive models such as SVM in our model training. This action can accelerate the convergence rate for our models. So this is the end of data pre-processing.
And after processing the data, we built 9 models to predict whether or not it will rain tomorrow. The models include support vector machines with linear, poly, and the RBF kernel, logist regression, card, random forest, gradient boosting, tree, and XGBoost. We also apply bootstrap to build the 95% of confidence interval. As it shows on the table, the accuracy of all the models fall in the range of confidence interval. For evaluation of the models, all models show better performance than the baseline model, in which we predict not rain with accuracy of 0.77. As it showed on the table, if we only consider accuracy as a matrix, XGBoosting is the most powerful model with 0.85 of accuracy. However, if we take both accuracy and runtime into account, support vector machine with polykernel is the best model with 25 seconds of runtime and 0.85 of accuracy.
Let me introduce the impact of our models. And for people, prediction on whether or not it will rain tomorrow help people adjust their ways to work and trip plans. And for agricultural industries, the prediction helps farm owners make necessary adjustment to the schedule to avoid economic loss. And for insurance industries, it can be helps them to avoid natural hazards. So thank you for listening.